So let me start by writing the word K-theory at the board, because it's the tradition of every talk, I think, at this conference. So, but if I speak about K-theory, I mean topological complex K-theory. It's nice that the audience likes this. So, some of you, yes. Okay, let me write it down. So equivariant. So okay. So but this is not the title of the talk. So let me write down a push-out diagram. Elliptic homology, equivariant elliptic homology. So some of you might already be thinking, where can this be a push-out diagram? And it's a push-out diagram in the infinity category of ideas. So this means if I want to explain this, I should, I guess everybody knows about this, but I should say something like K-theory and elliptic homology to kind of get into this. Okay. So let me recall some things about chromatic homotopy theory, because so far I think there was, Gijs and Grojnowski had some chromatic homotopy theory, but maybe not everybody is familiar with it. And I don't want to be getting depth into this, but so say we have an even periodic ring spectrum. So what does it mean? Even periodic means that the homotopy groups of R are of the form phi0 of R. And then we have a Laurent polynomial generator where it has to be 2. So all homotopy groups are 0 and it's even periodic. It's not always necessary to impose this, but it's very convenient because essentially we can most of the time forget about the grading, move everything to phi0. And kind of my main tenets of chromatic homotopy theory is to study these kind of things through the lens of formal groups. Okay. And to every such ring spectrum, I can associate a formal group over its phi0. And I don't want to give a general definition of what a formal group is, but I just want to say that essentially it comes from, so I have, again, look at R0 of the classifying space of the circle group, so this is my notation of the circle group. And, well, I have a map from, just a multiplication map, sorry, this goes the other way around, from the circle, and this induces a map like this. Okay, and if I want, I can even give coordinates to this, so this would be isomorphic to this thing, and this is isomorphic to power series in 2 variables. And then what a formal group law is, which is almost the same as a formal group, I send this to a certain power series in 2 variables. So this is what's called a formal group law, and this has certain properties like commutativity, associativity, and utility. And for example, I can, if I take K-theory, which is my favorite example here, take complex K-theory, this is one of this even periodic ring spectra, then the associated formal group law is x plus 1, y plus 1, minus 1. So it's a very simple power series. So in general, we can have no hope so one thing I should say is, so we can study these spectra through the lens of formal groups, but often it's also possible to go the other way around. So there's a bunch of kind of theorems and constructions like the non-trivial exact functor theorem, how you can start with a formal group, so such a power series, for example, how we can construct such a ring spectrum. But in general, it's hard to really write down formal group laws or formal groups, because usually it's not a polynomial like here, but it's like some infinite power series where it's just very hard to kind of write down explicitly all the coefficients. And so here comes the thing that if we go from one-dimensional algebraic groups, we can get a formal group. So I don't want to give a definition here again, but let me look at an example. So let me look at the algebraic group GM. So let me take another letter here. Take V here. This can be seen as this. And so if you don't like algebraic groups, you can say, okay, if I take spec, this is an anti-equivalence between commutative rings and schemes. So we can just take a hop of algebra here and take spec. This is the same as an algebraic group. Or if you also don't like this, you can also think for the moment about the C points of this, which is just the invertible elements in C, which have like an obvious multiplication. Okay. So, and actually, under this construction, this here is exactly mapped to this. To this formal group law coming from K-theory. And what does this construction do in this case? Well, we just Taylor expand the group law at the identity element, and there's a certain change of coordinates going from like this variable to 1 plus it to really move to the identity element, and then we have to move back. And this is exactly how multiplication translates into this formal group law. Okay, so we see that the thing we get for K-theory is exactly the one coming from this one-dimensional algebraic group. So we might want to repeat this story. And now this question becomes, what other examples are there of algebraic groups? And essentially there are just 3 examples of one-dimensional algebraic groups. Of one-dimensional algebraic groups. So one is what's called GA, the additive group, and C value point would be just C with addition. And this corresponds to the usual Einberg main spectrum. I mean, it depends, or yeah, maybe I don't want to specifically write it down because it depends on which base you work, but the corresponding base that can do it over Z, can do it over C, or whatever you want. And GA we just said, so GM we just said this corresponds to K-theory. And then there's a third family, which is called elliptic curves. And while these are more or less unique, well, elliptic curves, there are a lot of them. So what's an elliptic curve? So first in the, so this table didn't really make sense. So if you think about our C, it would be just a torus. So it's a curve of genus 1. And over C, you can always write this as C modulo lattice. I mean, you can take the standard lattice, so Z squared inside C, get a torus, but you can also modify the lattice and get a different complex structure on the elliptic curve, which counts as a different elliptic curve. And in general, you can say it's projective curve of genus 1. And if you come with a marked point, and this will induce a group law on this. And this will be the third family of algebraic groups. And it can be very explicit, you can really write down equations for everything. Okay. So you might ask, okay, can we repeat the story? And the answer is yes. So, definition. And elliptic homology theory consists of a ring spectrum R, an elliptic curve E, well, it's over pi 0 of R, so elliptic curves can be defined over any commutative ring. We just look at projective curves over this ring, plus an isomorphism between the formal group of R and that of E. And well, I mean, there are a lot of examples you can write down. So many of these come from, I mean, yeah, I don't want to be 100% explicit, but I say examples, e.g., there's an elliptic curve you can write down over something like some polynomial ring like this. This would be a universal elliptic curve with certain properties. And then non-Weber exact functor theorem would give you that the elliptic curve gives you a ring spectrum corresponding to this. But there are also many of these elliptic cohomology theories which don't come from non-Weber exact functor theorem. For example, you can, sorry, this is not really an example, but let me just have it here. And you can also take the second Morava K theory associated, so you can take the elliptic curve over Fp. And you can look at the formal group associated to this, and this can be realized by a Morava K theory. This would be also an example of an elliptic cohomology theory. So there are many different flavors. So here we would just have pi 0 is just Fp. Okay. So, so why should one consider elliptic cohomology theories? I mean, there are also historically several reasons. Maybe let me just say the words. So one is that in the perspective of chromatic homotopy theory, we often talk about the height of formal groups and the height of the corresponding cohomology theories. And the general picture is like if the height is bigger, it captures more information. We've seen this philosophy of different heights and different types of complexes, kind of more as in parallel, also in Christian's and Kreises talk. And K theory is a very nice theory of height 1. We want to have a very nice theory of height 2, and in general, elliptic curves, formal groups can have height 2. And the nice thing is we can really control a lot of these things via the explicit equations of elliptic curves. And even when there's like construction, one can do in some sense going to the limit, constructing a universal elliptic cohomology theory called TMF. This has been very instrumental in what we now know essentially the first 100 homotopy groups of spheres, for example. Another thing is there's something called elliptic Gepner, which is certain invariants of manifolds taking values in modular forms. And elliptic cohomology can be used to get a better understanding of this elliptic Gepner. So there's kind of two motivations one can consider. Okay, and any questions so far? Okay, so then I also should comment, this is like a 20th century definition, there's also a 21st century version of this. So variant of definition. Well, I mean, I wrote pi 0. I mean, this is of course an evil thing these days. I should really, and I didn't really specify what kind of ring spectrum I have. So I could also say, take an E infinity ring, R, and I guess this should also be even periodic, to make our life easy, plus an elliptic curve directly over R. So this is like the spectral algebraic geometry which allows to do us. I don't want to go into details, but it's possible, and plus an equivalence of like spectral formal group laws, formal groups, between the one I get from the even periodic ring, find spectral formal group over R, and the elliptic curve. And this gadget together is called, it's a definition due to Lurie, and this is called an oriented elliptic curve. Yeah, it would maybe be better to have like a parallel name here, but I mean this is the established terminology, and he used it to great effect, for example, to this notion to give us another construction of TMF, and for many more things, which we also come to later. And I should say these are also what Lurie does, gives plentiful constructions of oriented elliptic curves. So if you give me an elliptic curve, there are chances that I can lift it to such an oriented elliptic give me an elliptic curve over some ring, the chances I can find this E infinity ring R, which pi 0 is this thing, and I can lift the elliptic curve to this kind of thing. For example, for this elliptic curve I didn't specify, I can do this. This will be an example. Actually, this is not even periodic, but I mean, this is a minor thing. I can make it even periodic. And if I drop the E infinity here, just go to E1, then I could even do it for many more elliptic curves. For example, I could do it for this one I have here, and kind of get elliptic curve over more of a K theory. But just E1 because it's like a well-known fact that it cannot be E infinity. So questions?
Yeah. What is this spectral scheme over E1?
Yeah. So in general, I don't want to say this because I don't know. But so say you have a situation where pi 0, I mean the homotopy groups of your ring are commutative. Then you can take spec of the pi 0. I mean, and then you can take the sheaf of ring spectra on this. So I mean, I think it's tricky if you want to set up a whole theory, but like in specific instances, you can use these things. Okay. So I promised to say something about equivariance, so let me do so. And there's like maybe I shouldn't erase all of this. So there's a special connection between going to equivariant K theory and the picture I've drawn here. Maybe you might ask, so if you know the non-abelian exact functor theorem, you know that it's sufficient to know the formal group here to reconstruct K theory. But you might ask, so what about the algebraic group? Does it play any role? And the answer is yes, if we go to equivariant K theory. So let's start with equivariant K theory. Yes. You all know that if you have, say, X is a finite GCW complex, to not come into the issue Marcus has mentioned after his talk when I asked him about K theory, and G is some compact Lie group, so if always compact Lie group for me, then this guy here is just, you look at equivariant vector bundles over X and take the golden Lie group. So this is what it is. So in particular, we can look at this thing. Well, what is the G equivariant vector bundle over points? Just do G representation. And then this is RG, the representation ring. Just the Grothendieck group of finite dimensional G representation. And well, one knows the complex world, everything decomposed into irreducible representations. So this is actually, you can say, it's a direct sum. You get a copy of Z for every irreducible G representation. So let's look at an example. Namely, let's take GS1. So to be consistent, I should call it T. Let's take GS1. And we know precisely what the irreducible representations are. They are all one-dimensional given by rotations. So they're indexed by Z. So we get that R+1 is, I can write it like this, but the better way is to actually, this is like as Wheeling groups, but the better way is actually to write this as the Laurent polynomials to get the group structure. Okay, so you see this is exactly the same ring I have here. this might be a coincidence, but actually I also get the same group structure. So, so if I look at the map, the multiplication map on T, this induces a map from A0T point. We can restrict along this map here. So I will comment about this more a little bit later, but in K-theory we have also restriction maps for non-injective maps like this. We can just pull back the vector bundle, in this case representation. Well, turns out that this is, in this case, simple computation shows same as this tensor product. So we get a map like this. So you see, this really looks like a Hopf algebra structure. We can easily check that it's indeed a Hopf algebra structure. And it matches exactly the Hopf algebra structure we have here. So we really can recover the algebraic group. So this means that spec K0T of point is exactly GM. So we can recover this. And in a moment, what I want to explain about equivariant elliptic cohomology, well, so elliptic curves have, fortunately or unfortunately, depending on who you are not of the form spec of any ring. They are not affine schemes, projective schemes. So I have no chance to work completely in the realm of like rings and modules over this and stuff like this. So I have to interpret now everything in terms of algebraic geometry, and then I can say, oh no, we do an analogous thing in elliptic cohomology. So let me interpret a few things about equivariant K-theory in terms of algebraic geometry. I mean, this will be nothing deep, just a reformulation of obvious properties. But this will serve as a blueprint. So, namely, so if I have so I have a function of finite GCW complexes. Goes to modules or this guy. But this is actually equivalent to quasi-covariant sheaves on the spec of this. This is just the general thing. If I have an affine scheme, quasi-covariant sheaves, and this is just the same thing as modules over the thing. Okay. And moreover, so now I have these things. Well, what happens if I induce something up? This is the next thing I want to say. So if I have like, I mean, because this is, I didn't say this, but this is. So usually one would say that if I induce something up, then it's isomorphic to K0H of X. So X is an HCW complex. But this is not 100% true. If we say it takes values here, we have a restriction of modules going on here. So if we denote this by, do I have a good name? Let's just call it for one moment script K of this thing, then, well, restriction of modules corresponds to push forward between the schemes. It's just how quasi-covariant sheaves work. So we get that this thing is the same as the push forward of this thing along the map. And I guess let me see. So I have a map from spec So the map is contravariant, the spec is contravariant, so the map goes this way, and this is then the same as the push forward here. Okay. So this would be the fancy version. Now we're ready to do everything like this in the realm of equivariant elliptic cohomology. Now we have an idea what we would like to be true, and then we just have to show that it actually exists. Maybe I can start. Okay. So equivariant elliptic cohomology, and the idea is replace Gm by an elliptic curve. So I should say this idea is of course not new to me. This idea is already quite old, and so originally the first construction of equivariant elliptic cohomology was done by Grojnowski in '95, but everything was over the complex numbers. So you only consider elliptic curves over the complex numbers, so explicitly like C modulo 11. And then there was Ginsburg, Portano, Wasserwurf, which I think was also 95. What they did, they didn't provide any kind of new construction of it, but they said, okay, what axiomatics should equivariant elliptic cohomology satisfy, first of all? They showed that it's true for Grojnowski's one, but in principle this applies more generally. I mean, there's one mistake in the axiomatics, but if you ignore this, this implies. Then they showed how to apply this in geometric representation theory. So these guys were all motivated by representation theory, but this is like I think a different kind of story, which I don't want to tell, and I also don't know much about. So then, much later, I mean, there were some other people like Rochow and Greenleaf in between. Lurie, in '07, wrote a very beautiful document called Survey of Elliptic Cohomology, which is very inspiring, and there he sketched a construction how to kind of get equivariant elliptic cohomology from this theory of oriented elliptic curves. But I mean, let's say it's a bit short on details, and also doesn't he doesn't really give a theory which satisfies his axioms. I mean, they're not in contradiction to the axioms, but I mean he doesn't write them. I mean, what he does there, what he sketches there, doesn't give precisely this. It's like a bit. It's a different. It gets in some sense less, but I mean, yeah. Let's see. So and then there's also I should mention Berwick-Evans Tripathy. It was rather recent. I don't want to, maybe 18. So they also give a construction of a C, but now their construction works for all groups. This was just for connected Lie groups, and this now for all compact Lie groups, very uniform way, and they give a differential form model, which is, yeah, which is not exactly my style, but good to have. And then what I want to talk about is joint work with David Gepner. So we have one article out on this, and there's another one. Let's see what it appears. Okay. So let me explain what we construct. So we first, before what we construct, I should say what we start with. So we start with an oriented elliptic curve E over some R, some even periodic E infinity ring spectrum R. So this is our starting point. As I said, these are rather plentiful, and yeah. And if you want, you can even replace it. You can take here the modularized spec of elliptic curve and look at the universal one, but then I have to change a few things I'll write down later. But so let's just stick to the setting where we actually overgoing. So first of all, if we look at this kind of story, we have to replace spec of representation ring by something, like spec of K0G of point, because we want to take quasi-coherent sheaves on something. So for every group G, we want to have a spectral scheme If you don't know what a spectral scheme is, just think of a usual scheme with a sheaf of E-infinity ring spectrals in some sense compatible with this. But we want to kind of stay in this realm as long as possible. So more precisely, because we want, of course, that it's functorial in the group, so more precisely, then all the following category, namely the objects, are Lie groups, compact Lie groups, and the morphisms are homomorphisms, and the true morphisms is conjugation. Okay, so we can consider these two categories. It's in reality, of course, it's a topological two category because well, we have homomorphisms here, and we can pass to a corresponding infinity category. So more precisely, we have a functor from all two spectral schemes. Sorry, which sends each G to X. And then, okay, this is where we want to kind of constructing these kind of things from a point, and then we want to have functors which are called ELLG from finite GCW complexes of the quasi-coherent sheaves on the XG, exactly like this functor KG I've described there above. And the third one would be this compatibility if we induct out then. So ELLG HG should be equivalent to a push forward of ELLH X along corresponding map from X H to XG. If we fix a map from H to G and X is an H to W complex. And if one wants, one should really work in this framework of sort of Orbi space, which makes this kind of properties automatic and give kind of all the coherences one wants to have in this equivalences. But let's just stay with this.
And you said in the map from H to G, you want to inject it in here, or is it only for all homomorphisms?
I think this is just true for all homomorphisms.
I think if you wanted to be the push forward, be for the injective ones. Otherwise, don't you have just a map?
Comparison map you should always have, yes, but is it equivalence if it's not injective?
Let me see. Let's just stick to injective. Yeah, I think injective. Let's just take injective, yes. Mm-hmm. Right, yes. And the map one wants always to have the map, but not always. Okay, so this is the theory we construct. And now this is like not the usual kind of Chromology theory, because you have you go into quasi-coherent sheaves on some spectral scheme. And this is not the usual kind of cohomology theory. And there are just two, I mean, there are two different ways how one can make it more classical. And I will also, I mean, this I have to explain how to make it more classical, and I should also tell you something about this xg, because it's a bit like, it would be a bit frustrating if we just have a pure existence without.
The construction that sends G to xg does not depend on the elliptic curve E, but
No, it certainly depends on the elliptic curve E.
X just depends on E and the association LG.
Yeah, this will become apparent in a moment when I say tell you what the xg are in some cases. But this all heavily depends on the elliptic curve. I just hit it from the rotation. For example, if you take G to be the circle, then xg will be exactly E, which depends on it. So two ways to make it more classical. So we said we start with finite GCW complexes. Oh. Go to here. So some people want to have cohomology theories taking values in the abelian category, so like 20th century cohomology theory. So well, we can just take homotopy groups of this quasi-coherent sheaf on the spectral scheme. And so underlying, so let be xg half be the underlying classical scheme. And then, well, we just go into quasi-coherent sheaves on this thing. So for example, if G is a circle, we just quasi-coherent sheaves on an elliptic curve. So this is the setting also Grojnowski works in. And this is then a classical kind of cohomology theory from here to here. I mean, I didn't say this, but this functor, I mean, is excisive, so usually cohomology theory properties. And actually also next symmetric monoid, I didn't say this. Okay, so this would be a classical cohomology theory. And the other thing is, I mean, I can take global sections and just go to spectra. This was something which would not be available if I didn't work in the derived setting, because, well, take global sections not exact. And if I want, of course I can. If I really have to, I can go further to be.
Not your style.
Sorry, what is that?
It's not your style.
Okay, so I get a functor from here to here, and in fact, what is a nice fact maybe is that, so here I have the, no, this I shouldn't say. Let me say, okay, so actually it would make more sense not to go to spectra, but go to R modules, because it turns out everything, well, everything lives over R, where R is the thing that elliptic curves lives over. And it turns out, and let me do I find a green chalk? I will have to take red chalk instead. It will always take values in dualizable R modules. So this is the theorem I proved stated. And this may be coming as a surprise if you think about this K theory. So if you take equivariant K theory, you look like at maybe I should write down something. If you take K0G of X, well, this is not always a finitely generated leading group. For example, if G is finite, then yes, then it will be always finitely generated. But if G is compactly, like G is S1 and X is a point, then it's an infinitely generated abelian group. But here we have finiteness for all compactly groups. And the reason behind is essentially because elliptic curves are compact or proper.
Sorry, shouldn't it be like the finiteness shouldn't be equivalent to be finitely, presented as a module over K0G point?
Yes, but this would imply that it's a finitely generated abelian group.
No.
You take.
We want it over R. That's just a non-equivariant case theory example.
So what I mean.
Oh, R is not the global section.
No.
It's just the general base.
Yes.
I see.
So sorry, I didn't hear what you said there. It would be an analog of this non-only dualizable module over non-equivariant K theory. Okay. So this is a nice property having to do with elliptic curves are basically compact. So like if you look at very classical like global sections of homology group of a coherent sheaf on an elliptic curve or vector bond, let's say, well, this will be a finite dimensional C vector space. And if you this is the property we're kind of leveraging in a more fancy context.
Oh, so sorry. So essentially, what you have is the finiteness over Q co, and then you use progress of the push forward.
Yeah. So we use that. Well, yes, that is xg are always proper.
Yeah.
And then one has to be a bit careful, but check some things, assumptions, and then it falls out. Okay. So this is about the general properties and how it then this is like a more or less kind of classical equivariant homology theory, taking values in abelian groups. With all the finiteness properties, one more. Okay, so now I have to also tell you something about what these xg are to be a bit more concrete. So the first one is xt is exactly the elliptic curve we start with. So turns out if G is abelian, then xg will always be homomorphism from the Pontryagin dual to E. So this is the Pontryagin dual. So this is always like a discrete group. So say a circle, I get the integers here. So I can just check homomorphism from the integers i.e. again. So that's good. So for example, if I take torus, higher dimensional torus, I will just get a product of several copies of E. So where does this formula come from? Well, if you take the representation ring, so K0 G of a point for G abelian, well, the irreducible representation are all one-dimensional. So what I just have, I take the direct sum over the Pontryagin dual, because these are exactly one-dimensional representations of Z. And if you think one moment about this, you will actually figure out that if you take spec of this will be exactly Hom from Pontryagin dual to Gn. So here the formula holds.
So this Hom is in some category. In which category is this Hom?
Well, I mean, so the pedestrian way would be to say, if you take Hom from a product of Z's, you just get these copies, and else you can present your group and then take a corresponding fiber. So, for example, if you have X Z mod n, well, Z mod n is like the Pontryagin dual is isomorphic to Z mod n. So we can present it like this. So what we get is that X Z mod n is the fiber E multiplication by n E, so exactly the n torsion in the elliptic curve. Okay. Okay, this is the abelian case. And from non-abelian case, well, in general, I think there's no hope of giving a good description the non-abelian case, because, like, say I give you an arbitrary non-abelian group, can you describe the representation ring? a bit hard. I mean, this would kind of, in some sense, this would at least encompass all of the representation theory of finite groups. And for example, even like something which is.
But could we try to go to maximum torus and look at the y? Exactly.
If your D group is connected, then you have much better chances. Yeah. And so if your D group is connected, you have much better chances. And this is the case I want to say a little bit about this. So there's a classical theorem which says take representation. So if G is now connected completely, there's a classical theorem which says that the representation ring of G is the same as the representation ring of the maximal torus, and representations of tori are well understood. Then you take invariance and a so-called Weil group. Weil group is takes the normalizer and mod T, this is the finite group. And so you might hope that something like this is true. So if it takes the xg, then this should be the quotient xt by the Weil group, because it takes spec, taking invariance corresponds to taking a quotient. So there are several problems of this. First of all, what does this mean? You don't want to take a stack quotient here, it will be a quotient in schemes. And even this is not completely the correct thing, but you might at least hope that in underlying schemes this is correct. And one thing I proved also with David, I think I have to watch a little bit of time. So one thing I proved with David is to take the underlying scheme of the UN invariant thing, this is exactly the underlying thing of the torus, which is like just a product of elliptic curves, model the Weil group, and the Weil group in this case is the symmetric group. And we even prove a better statement, we actually identify this as a spectral scheme, but this would be a bit harder to state. And actually this thing would be unreasonable for elliptic homology to expect in general.
Sorry, but now you haven't given us the definition of the left-hand side, so this could be topology.
Okay. Okay, so let me first give you the definition. So you can what I've written down above this formula can be promoted if you think a bit about this to functor from abelian orbits to spectral schemes. Then you can go to the whole orbit category. And in fact, you can let the Kahn extend this. This is not obvious at all, because, well, this is not a co-complete category. But we show that this left Kahn extension exists. So we first go to set to spectrally locally ringed spaces, kind of construct the Kahn extension there, and then show that it always a spectral scheme by reducing actually the case of UN. Now I've given you a definition, and then we prove this, and even give like a more concrete construction here. For general G, one should not hope, well, one should not hope that this is true. Essentially, the point is that the representation, so in the setting of K theory, is determined by its character. The character depends on conjugacy classes of elements. And I can conjugate every element into the maximal torus. Actually, conjugacy inside the maximal torus is exactly determined by the Weil group. So this sounds like a reason, I mean, this is not a proof, but I mean, this is a reasonable statement. And the general philosophy says, which also like there are theorems saying this, that in elliptic cohomology theory, we shouldn't look at conjugacy classes of elements, but of pairs of commuting elements. And in general, a pair of commuting element cannot be conjugated to maximal torus. This only happens if pi1 of G is torsion free. This is a classical theorem of Borel. And in this generality, if pi1 of G is torsion free, I would conjecture this is true, and then we have yeah, we have an idea how to prove it, but I tried to prove it yesterday during the talks, but then the talks were too good, and then I couldn't do it. Yeah, I would hope that pi 1 g cosmos b this is true. But, yeah.
That it's two commuting elements is because elliptic homology is pi 2. Or, I mean, what's
Yes, you could say this, yes. Yes, this one, I mean, there's classical work of Hawkins convolutional would be one motivation, but you can also make it more concrete geometric arguments. This is what we expect. And you can actually show that this function here is left Kahn extended from a thing where you have only the abelian groups where pi 0 of it is just generated by two elements, and this is like further evidence for this. I think this is everything I wanted to say. Thank you.